awesome source. One more example in a widget factory, because we all know what widgets are, right? Excellent. Just for the video, everyone nodded enthusiastically when I said that. It produces 10,000 widgets a day. A sample of 10 widgets was taken. Shouldn't say at, it should say and 3 were found to be defective. Okay, so we have a sample of 10 and our attribute is defectiveness. So we've got a sample of 10, 3 were defective. What would the sample proportion be? Yeah, 0.3. 30%. So that's pretty high defective rate, isn't it? So imagine, like, I know this is not for realsies, but imagine you've got a situation where you're running this factory and you're doing a bit of quality control. So you grab 10 off the factory floor and test them, and you find, oh, shivers, 3 of them were defective. That's like 30%. Are we in trouble? So what we need to do is we need to take a larger sample size to determine whether actually is that reflected in this widget factory. You know, is that 3 out of 10? Is it really 30%? Are we going to find 30% are defective in this factory? Because if that's the case, let's shut down the factory and figure things out, right? So that's what brings us to the second part of the question. How many widgets would need to be sampled in order to confirm this defect percentage? And here's the bit that's the key thing then, because we just did confirm it, right? But 3 out of 10 is not a great sample. How many would we need to sample in order to confirm it with a margin of error of 5%? So now we've got a target margin of error, and we need to work out, well, what's our sample size based upon that target? And we also need a confidence level. So let's just say we want a confidence level of 99% and a margin of error of just 5%. Okay? Am I making sense so far? Anyone got any questions about the setup? Just to confirm, the expectation is if you are not following on with me, then you are in fact doing your methods for work, not rando work. So here is the solution. P hat we just talked about equals 3 out of 10, which is 0.3. That's not a problem. We know the confidence interval is 99%, and so we can draw our little standard normal and put in our edges here, and this is our 99%. Remember that means it's the middle 99%. And if it's a middle 99%, and the fact that it's symmetrical means that the tails are 0.5% each. Now, just to reiterate what I said last lesson, what we are doing is we are now sidestepping from the facts that we've got in order to work out the Z value that we need for the margin of error. So we're putting a pin on this, and saying, well, how do I work out a Z value? And the Z value is worked out by using our calculator, and we go Z equals inverse norm, and then we put in our our values for the inverse norm. And we remember, I hope, that what the inverse norm function requires is the top end all the way back. That's what inverse norm requires, all of that area. So the top end is going to be this 99% I'm scribbling on now, plus this 0.5% down here. So the top end all the way down is going to be 99.5%. That is what we need to feed into the calculator, and it will give me what that edge is there. That's what we need. We need that edge. So our calculation becomes inverse norm 0.995, 0, 1, and that gives us a value. Now, I'll just do it on the calculator. The more times I do it, the more I feel it might help us all sort ourselves out. Menu, probability or statistic, doesn't really matter which one you go to. Then we go to distributions. And then we go to inverse normal. We put in the target area, which is 0.995. We leave mu and sigma as 0 and 1. So I can go straight to enter. Press it twice, and out comes 2.58, which is what I'm going to write down, although I'm going to use those calculations over and over again. So here's where it gets different. Therefore, 0.05 is the margin of error, our target margin of error. So instead of saying m equals, we're going to put 0.05 equals, and then we're going to fill in the rest of the information that we know. We know the z value is 2.58. We know we're multiplying it by the square root of p hat minus times 1 minus p hat. So that's 0.3 times 0.7. And what we don't know is the sample size. So we're using exactly the same equation, but we've got a different unknown. Okay? And the rest of it is dealing with that. So for example, I'm going to flip sides and I'm going to divide both sides by 2.58. So I know without using my calculator that 0.3 times 0.7 is 0.21. I hope you know that as well. So on the left-hand side, because I've flipped sides, I'm going to have 0.21 over n and square root it. And on the right-hand side, I'm going to have 0.05 divided by 2.58. So I literally go 0.05 divided by, or I can use my division button here, and then I'm going to go up until that's highlighted and press enter and press return. It's really important that you use this and not just 2.58. It can make a wild difference. So that gives me, and I'll flick over to my whiteboard in a second, 0.0194. Again, where possible, write down 4 decimal places. Apart from the z value, it doesn't matter so much. 0.0194, like so. So that's all good. What's my next step? Anyone who's paying attention? Yep, square away. That'll undo the square root. Back to my calculator. Sorry for my continual flipping. Again, using the full-on option and not the approximation. Squared. Enter. This is hard to write down, but again, is anyone else surprised to see that when I square this decimal number, I get almost 3.8? That's surprising, isn't it? Because it's not 3.8, right? Look down this is the bit to be careful of. E to the negative 4. And that means move the decimal point back 4 times. So I'm going to have 1 move to the end of 3 and then 3 more zeros. So that'll be 0.00037, so 4. Okay, so that decimal point goes back 4 times. I'll flick over so you can see it. All right, so be careful of that. If it's in scientific notation, that means you have to move the decimal point based upon e to the minus 4, back 4 places. If it was e to the plus 4, be forward 4 places. So be careful of that. Now what? Yep. I'd probably do this in one step, but I'll do it in 2 steps just here. I'm not going to touch my calculator yet. And then finally, or second from last, I suppose. divide both sides by 0.04, sorry. So I'm going to go 0.21 over 0.0004. So as soon as you see this, it's going to make more sense with the number we've got. If we're dividing by a really tiny number, we're going to get a big number out, okay? So just be mindful of that. I think it's always good as a mathematician to kind of be broadly aware of what numbers you're getting out of an example, out of a calculation. I mean, I don't know, looking at that, I can't tell you whether it's going to be 100 or 500 or 1,000, but I'm expecting a big-ish number, right? Knowing that, doing that kind of thinking just allows you to make sure that your calculations make sense. So 0.21 on my calculator is the top. I'm dividing by, and again, use the full-on number here. Makes a massive difference to your answer if you don't. Press enter, and there we have 557.3. Oops. 0.33, I suppose we'll do. So that is the number. And just off to the side here, just so I'm not flicking to other pages, i.e. use a sample of what? Yeah, good one. Not 557. That would not quite give us a margin of error of 5%. It's better to have a smaller margin of error than a bigger one, right? So we would use a bigger sample size, because I wanted to remind you that, remember from our work from our previous, I might just flick to it in a second once people have had a chance to write down, from our previous work, there are two ways you can modify the margin of error. One way is, not modify, but one way that reduces the margin of error. One is if we've got extreme results, like nearly everything or nearly nothing has the matching attribute. And the other thing that makes a massive difference is if you use a large enough sample size. So I'll conclude this, and then I'll just click onto those other two to remind you what that means. So what that means is that the factory workers or the factory boss then knows that if they take a sample size of, say, 560 odd, and they get a 30% defective rate as well there, then that's confirming that within a 5% error, it looks like about 30% of their factory is stuffed. So they better shut down the factory and sort out the problem. Does that make sense? Okay, so just to remind you then, really quickly, if I can, if I've got the right spot. Yeah, so in a previous video, if p hat is really big, in other words, the proportion is really big, our confidence interval is the interval is quite a small range. Or if I increase the sample size, e.g. from 200 to 2,000, my confidence interval is quite small as well. Okay, so just a reminder that that's key, is that if we want to get more confidence or reduce the margin of error, we really need to increase our sample size. And the last thing I'll say, and stop apart from questions, is, what was I going to say, team? Did you notice all the way through this solution, everyone's okay with this so far? Has anyone got any questions about that process? Kind of made sense? Did you notice that I never used that fact there? That there were 10,000 widgets a day? So technically, I could go, let's just say if I made this a widget factory produces, 558 out of 10,000 actually doesn't seem too unreasonable, does it? Like 10,000 is a lot. So taking a factory, a size of 558, although it would be tedious, seems reasonable in the context of it. But I could have written this problem exactly the same, except it had 500 widgets a day. And you'd see that for 500 widgets a day, the calculation would be the same, and it'll be saying you need a sample size of 558, even though they're only making 500 a day. What does that mean? It means that sometimes to get the confidence interval that you're looking for, the only way of really doing it is to do it for the whole population. But if the population is large, like 500, even 500 is not that big. If the population's large enough, your sample size is always going to be reasonably proportioned for your overall population. But keep that in mind. Again, it's a pretty nuanced point. It's just a point at the end. But your sample size that you're looking for is independent of the population size. Yes. Well, remember that the normal P in inverted commas is what we are assuming for a large population. We start by saying, well, if we assume P hat and P are the same, how confident can we be, I suppose? Okay, so in this instance, yes, we are assuming that, but if I actually calculated it based upon a sample size of 10, then the margin of error is actually going to be really huge, right? Because really, to get a margin of error of 5%, this calculation here says that, well, N would have had to have been, 560 to get that margin of error of 5%. So if you can imagine I did exactly the same process, but had an M here and had N as 10, then the margin of error is going to be much, much bigger. And that kind of sounds right too, doesn't it? Really. So in other words, if I'm going to assume that P hat is the same as P, when I've got a small sample, then my margin of error is going to be really huge. But if my sample is big enough, then my P hat and my P, it's a more reasonable thing to say these two things are the same. I like that follow-up question. Does anyone else have any questions?